Hello, in this section we are going to talk about the terms specific heats, CV and CP. So the specific heat, so we'll start by the definition of the specific heat. So the specific heat mainly is the energy required to raise the temperature of a unit mass of substance, so of 1 kilogram of substance, a unit mass of substance by 1 degree. So as we know, different substances need different amount of energy to raise their temperature by 1 degree. So this specific heat has different values for different substance. So what the subscript V and P mean, so for CV, the energy supplied for the unit mass of substance should be done during a constant volume process. So in order to raise 1 kilogram of a substance by 1 degree, we need to supply energy during a constant volume process. So this amount of energy will be called CV. So however, for CP, the energy supplied to the substance should be during a constant pressure process. So the subscript P means during a constant pressure process. So usually CP is greater than CV, since in a constant pressure process the substance is allowed to expand. So the energy supplied will raise the temperature of the substance, and the substance, part of the energy, the substance will use it in order to expand. So we need to supply more energy to raise 1 kilogram of substance by 1 degree. So that's why we define the specific heat capacity ratio K, small k, which is equal to Cp over Cv, which is usually higher than 1. It is equal to 1 for incompressible substance, and we will discuss it later on. And so if you want to talk in from thermodynamic point of view, and we want to define Cp and Cv in terms of thermodynamic properties, let's take, for example, a fixed volume. So a tank has a fixed volume and it contains 1 kilogram of helium, and we want to raise this 1 kilogram by 1 degree Celsius. So this contains helium. CV for helium is equal to 3.12 kilojoule per kilogram Kelvin. So the unit for CV or CP is kilojoule per kilogram Kelvin. So the amount of energy in kilojoule in order to raise the temperature of 1 kilogram of substance by 1 Kelvin. So this process we need to supply, if we look at the value of CV for helium, 3.12 kilojoule for every kilogram to raise it 1 Kelvin or 1 degree Celsius. Since this is delta T, so it doesn't matter if delta T in Kelvin or in degree Celsius. So the total amount of heat needed should be equal to 3.12 kilojoule. However, during a process at constant pressure, as in a piston cylinder assembly, so the piston is allowed to expand. We have here a mass of 1 kilogram. The pressure is constant, and delta T is equal to 1 degree Celsius. Cp for helium is equal 5.19 kilojoule per kilogram Kelvin. So that's why Cp is higher than Cv, because so here we need to supply 5.19 kilojoule. Since when supplying this energy, part of this energy will increase the temperature of the substance, and the other part will be used by the substance to expand from from volume 1 to volume 2. So the substance will expand. So we need to supply more energy when heating a 1 kilogram and trying to raise the temperature by 1 degree Celsius. So let's first, for the constant volume process, let's apply the first law of thermodynamics. We will have delta U equal Q, delta U from, let's say, 1 to 2 equal Q from 1 to 2 minus W from 1 to 2. So here the work is 0. So now Q from 1 to 2 should be equal to delta U from 1 to 2. We can write this equation in differential form. And we can say delta Q from 1 to 2 is equal to the du, and the amount of energy supplied, so this is written per unit mass. So del Q here, so the total amount of energy per unit mass supplied should be equal, so since this constant volume process, should be equal to Cv dt. So this equal to du. Then we can say that Cv is equal to del U over del T at constant volume. So this partial derivative should be evaluated during a constant volume process. And if we apply the first law of thermodynamics for the constant pressure process, it will be delta U from 1 to 2 Q from 1 to 2 minus the work from 1 to 2, and here the pressure is constant, so it's P delta V from 1 to 2. So Q, the amount of heat supplied, is equal to delta U from 1 to 2 plus P delta V from 1 to 2. So delta U plus P delta V is delta enthalpy from 1 to 2. So we can write this equation in differential form. And of course per unit mass, and the total amount of energy supplied is equal to Cp into dt per unit mass, so should be equal to d enthalpy. So we'll have now the definition of Cp is del H over del T during a constant pressure process. So now the specific heat at constant pressure and at constant volume can be written with respect to thermodynamic properties. So here of course Cv and Cp, they both depends on the temperature and the pressure, since as we know the properties of internal energy and enthalpy depends on temperature and pressure. So these values or these properties, Cv and Cp, can be used to evaluate the properties for solids and liquids, for example. So Cv and Cp can be used to evaluate properties of solids, liquids, and ideal gases. For ideal gases, we will discuss them later in coming sections. But now I will talk about how to use Cp and Cv to evaluate the properties of solids and liquids. So we said before that for solids and liquids, we said before for, let's say for liquids, we use approximations to evaluate their property. We said that the specific volume can approximate it as Vf at T, and the internal energy approximately Uf at T, and we can say the enthalpy also is Hf at T plus the term Vf T into P minus P sat. But usually this term is negligible, and however, if it is not negligible and it has significant values with respect to HFT, we can leave it, but usually this term is negligible, and we can say that H is approximately Hf at a given temperature. So for liquids also we can use the values, so we can evaluate properties for liquids and solids also using specific heats. So this is another way to evaluate the properties of liquids and solids. So how we do that? We refer to the incompressible substance model. So the incompressible substance model is based on observations that liquids and solids, their energy, their internal energy, and their specific volumes varies little with the pressure. So for the incompressible substance model, it says that the specific volume and internal energy of solids and liquids vary very slightly with respect to pressure. So we can say, in other terms, the specific volume is assumed to be constant. So the density, mainly the specific volume, or the density, which is inverse to the density, we can assume in this incompressible substance model is assumed to be constant, and the internal energy varies only with temperature. So we can summarize this as follows. So the specific volume is assumed constant, and the internal energy depends on the temperature only. So for liquids and solids, based on observations, assuming the specific volume or the density is constant and the internal energy depends on the temperature only, is a valid assumption. So now the specific heat CV, so for the specific heat CV, since the specific heat CV is defined as del U over del time, del temperature, since the internal energy solely depends on temperature, we can say that CV, so CV becomes now du over the temperature, since U is function of temperature only, and the V, the specific volume, is always constant. So now for the enthalpy, H, as we said, is U plus PV. So if we do the derivative of these two quantities with respect to temperature during a constant pressure process, so U depends on, so this will be du over dt So U depends on temperature, so total derivative, partial derivative should be the same, plus PV. So P is constant, and the derivative of the specific volume is 0 since the specific volume is unchanged. So now Cp should be equal to Cv and is equal to C. So for solids and liquids, we don't have difference between Cp and Cv. So Cp is equal to Cv, and K, which is Cp over Cv, in this case will be equal to 1. So we can say now, if we want to calculate the change in, so du, we said it's Cv dt. So if we want to calculate the change in internal energy from 1 to 2, and here from U1 to U2, and here from T1 to T2, we can say that U2 minus U1 is equal to Cv T2 minus T1. So this, of course, assuming that Cv is independent of temperature and is equal to a constant. So for the internal energy, so since Cv is just C, you can always say that it is C T2 minus T1 also. So this, you can calculate the change in internal energy for liquids and solid, for mainly incompressible substance, as C delta T. So we just need to know the values of C and the values of the temperatures during the process. For the calculation of the enthalpy, so dH equal du plus pdv plus vdp. So since in the incompressible substance we assumed that V is constant, so this term should be equal to 0, and if we integrate H1 to H2 and U1 to U2 and P1 to P2, we can say that H2 minus H1 is equal to du, which is C T2 minus T1, plus, since assuming the specific volume is constant, so it is V P2 minus P1. So mainly this term can also be neglected, since the specific volume is small for liquids and solids, and we can say also H2 minus H1 as C T2 minus T1. You can use table A19, so table A19 as in the attached thermodynamic tables PDF, so table A19, to extract values of specific heat for some selected liquids and solids. So if we go to table A19, so this table include specific heat Cp, density ρ, and thermal conductivity for selected solids and liquids. So here we have Cp, but Cp is equal to Cv and is equal to one common value C. So this is the term specific heat for selected solids and some liquids. So you can see at the end water at different values of temperature. A specific heat mainly depend on temperature. However, the variation of the specific heat with respect to temperature is relatively small. So you can see a temperature of 275 and at a temperature of 400 we have a difference of 125 degree. So the variation is from 4.211 to 4.256. So mainly assuming C as constant will yield good accuracy. So we will not lose a lot of accuracy if we assume a constant value for C. What I recommend, if you have a pure substance and it is undergoing a change between a temperature T1 and T2, you can always take C as the average value between T1 and T2. So it is C1, which is evaluated at T1, plus C2, which is evaluated at T2 over 2. So in this way you will have accurate values.